Today we want to look at MOSFET behavior as mathematical law. The last class I taught you inequalities. Now, why am I teaching this series? This is to encourage mathematics students to take their mathematics courses very seriously, right? It is the best course on earth. You know, Elon Musk has said it is advisable for you to focus more on learning mathematics and physics than to learn coding because AI will handle that part. But if you don't know it, you will probably not be able to appreciate what the AI is going to give back to you. So you also learn coding, but focus more on mathematics and physics. So that's why I'm doing this series for you to appreciate what you are learning. So I told you that inequality actually exists in the symbolic layer of mathematics and also at the operational layer of mathematics. Now, at the operational layer of mathematics, inequality performs action, right? The machines obey inequality. Machines don't obey equality. What do I mean by that? It is difficult for machine to understand voltage equals to 5 volts. It is difficult. Why? Because equality deals with identity. Inequality deals with judgment. And reality is continuous, right? So it is a process, it's a gradual growth. So machine rather prefer inequality because that is what they can actually understand. So machine will deal with what? Voltage is greater than or equals to what? Threshold, right? This is what machine will deal with. If the voltage is greater than or equals to threshold, machine will perform action, right? So that is what this is. So what I want to do in this class is to use this guy to explain how inequality is converted into what? Physical permission. Mathematical inequality is converted into physical permission. So how does it do that? It uses this device called MOSFET. So what is MOSFET? MOSFET is metal oxide semiconductor field effect transistor. It is a type of transistor. And I told you that your CPU, which is the central processing unit, is made up of billions of transistors. So I'm just going to extract one and use it to explain the concept. So this is it, right? This is it. This is my MOSFET. So I'm going to draw this. Don't mind my drawing. So um, I'm going to use N channel MOSFET. So I'll put a load here. So let's just put as if it is a bulb. Then I bring this here, 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 here. Then I draw this. Then I bring this here, 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 here. And I draw this. All right. So this place is my what? Drain current. This is my VD. And then this is the load. So this is the drain, this is the source, and then this is the gate. So this guy is called VG, right? So this is the transistor. It's a device that converts mathematical inequality into what? Physical permission. You know, inequality, machine is dealing with, um, machine doesn't deal with identity. Machine deals with qualification. Does it qualify? Right? That is what machine is dealing with. So that's why we have threshold. So there is a threshold voltage created inside this transistor. I taught you threshold in my first class. So let's say that the threshold voltage is VT and is what? 1 volt, right? So if this voltage crosses this threshold voltage, then this transistor will begin to conduct and then current will flow and this guy will come on. Don't forget, voltage doesn't flow inside. Voltage is what? Potential difference. It is the force that helps to push current, right? All right. So VT equals to 1 volt. Now, the equation will now be VG, right, greater than or equals to what? VT. But this would divide reality into two what? Three layers, which is what? Cutoff layer, cutoff, linear, the cutoff zone, linear zone, and then saturated zone. Saturated zone. So for the cutoff zone, right, it means for the cutoff zone, VG is less than what? VT. Because if VT, that is the voltage required for this transistor to switch on, for current to flow, is what? VT. If VG is less than VT, it will not come on. It means that ID, which is this current, is approximately equals to what? 0. Right? So that is the cutoff layer. That is the cutoff layer. So for the linear layer, it means that VG will be what? Greater than or equals to what? VT. Which means that the current, which is what? ID, will be what? Directly proportional to what? This equation can now be written as what? VG, right? Minus VT, right? Is greater than what? 0. This equation can be written as this. This voltage is called overdrive voltage, meaning the surplus, the difference between the VG and the VT. So if VG is 2 volt, if VG is 1 volt, right, 1 volt, and this one is also 1 volt, it means 1 minus 1, that is 0, 0. If VG is 2 volt, right, and VT is 1 volt, that is 2 minus 1, that is 1 volt. So the surplus voltage, which is what we call overdrive voltage, VG minus VT. So current will be directly proportional to what? To that overdrive voltage. So that is at the linear level. That will give us this linear, right? But as we go on, this will be squared, which means current will be directly proportional to what? To the square of what? The overdrive voltage. These are equations that is outside of the scope of this class. But what I'm trying to make you see in this class is to see how this device, right, converts the mathematical inequality, which is what you are looking at now, into what? Physical permission. Meaning, the moment we cross this voltage, once it is true, then go ahead and perform this task. So if we are going to draw a graph for it, it will be something like this. This place will be what? VG. This will be what? Our drain current. So let's have VT here. So which is what? Threshold voltage. So this is 0. So VG less than VT will be what? Off. While this side will be what? On. This side is on, this side is off. So if VG is less than VT, right? It means it's going to give you, it will be less than the threshold voltage. So it will be at this point. Then the moment VG is greater than what? VT, it will begin to conduct like this. So as it goes, then it will cause this parabola, which is what? This. This is the point. So this is the continuous state, and then this is the saturation point. So the machine is going to use this point and this point to decide on or off, which is what? 1 or 0. So in a nutshell, what I'm telling you is that your mathematical equation will have to be converted into code using programming languages. Then this code will be scheduled by the operating system, which means authorization is given in terms of how sequentially the authority is going to function. That will be stored in the memory, and then the CPU will go to take it and then act. So that your source code signal, right, that is coming from your program is this part. So the signal is going to this guy to trigger it. But you know you have written a program in mathematics, you have written a code. But when it gets to the machine level, you are having electronics components there, and you are dealing with what? Voltage. You are dealing with voltage. So the mathematical equation that you have converted into programming code will now have to what? Manipulate or control this voltage to work in a way as to cause the load to come on or stay off. So you can see the relationship. So mathematics students, I'm just doing this to encourage you to understand how important what we are studying is. That everything in life is what? Applied math. Every engineering is what? Every branch of engineering is applied mathematics. Now, every branch of mathematics is also applied, but not every branch for now of mathematics is applied. Science is still studying. So you have some mathematical equation, but we do not have technological application for it yet. So all what we are doing with technology is what? Applying mathematics, right? So this is what I want to show you in this class. Don't forget to like, don't forget to subscribe if you have not done so. So now that I've shown you the practical application of mathematics, we can now go to the symbolic layer of mathematics to study the different branches, right? And then as we go on, we continue to apply them so that I'll be showing you the examples of how this mathematics is useful in machine. So, till we see in the next class, bye-bye.